one is phase. And so for the phase fluctuation, however, it is so that because it's a charged medium, what happens is that you have to introduce also vector potential. And if you do a standard gauge transformation to your vector potential, this phase will be eaten up by the vector potential. And then if you also include a long-range Coulomb interaction, your phase fluctuation will also be a gap towards become a plasmon excitations. So this is all very well known, and this the excitation at the 2 delta in our community is called still a Higgs amplitude fluctuation. Although the true Higgs mechanism is actually connected, in fact, to the gapping of the phase fluctuations. Anyway, so the microscopic theory for the conventional superconductors, that the conventional methods, is also has been developed in 1956 by Bardeen, Cooper, and Schrieffer, where they understood that you can understand the formation of the Cooper pairing, despite the fact that the electrons are typically experience repulsion in a solid. You can also have an attraction, and the attraction you do because in this case you have a ionic lattice which is positively charged, and therefore the idea is that electrons which are moving into opposite direction. So the first electron introduces a local deformation, and the second electron after a long time, and this is important, that this is the retardation effect, that this attraction due to the phonons can only occur over the long time period, will yield the formation of the bound pairs, which is known by now as a Cooper pair. And in total, you can consider this, make a full analogy to the hydrogen atom, where you can form bound state, and in this case, you describe a bound state of 2 electrons in a Cooper pair in exactly the same way. So it means that you introduce the bound state and introduce the corresponding symmetry, and the simplest symmetry you can first imagine is the S-wave symmetry. This is the first state that you get the highly symmetric state of this bound state, and this is allowed by the attraction, and this is what we believe happening in most of the conventions. Okay, very good. So now what about the unconventional superconductor? So traditionally the understanding was that in unconventional superconductor there is at least one other symmetry other than gauge symmetry is broken. And that could be, for example, the symmetry group for crystal lattice. For example, if you have a bound state of a Cooper pair which has a D-wave character, then the D-wave symmetry has lower symmetry than the original symmetry of the lattice or the original symmetry of the Fermi surface, and that is why would be one classification of the unconventional superconductor. If we are dealing with a spin triplet superconductor, because the most simplest one that BCS assumes that you have a spin up and spin down or spin singlet state, you can also have spin triplet configuration. That in this case you would break a spin rotation. Other situation that we also know that there could be if you have a multi-component order parameter. So it means you have a irreducible representation of the point group symmetry, which is containing 2 wave function that can also have a state which breaks the time reversal symmetry. And that has definition worked pretty well until the discovery of the iron-based. However, in iron-based superconductors, strictly speaking, the symmetry, there is no additional symmetry that is broken. Nevertheless, we still believe that this is an unconventional superconductor because it was not driven by the electron-phone interaction. Therefore, now the conventional notation is that that unconventional superconductivity is the one which is not driven by the electron-phone interaction. Okay, so here I made you a brief history of the field, and as you see, that's very dynamic. So of course, it originally started from the discovery of superfluidity in helium-3, which is a fermionic liquid, by Osherov, Richardson, and Lee. And of course, it doesn't have phonons. Therefore, you would need a mechanism to describe superconductivity there without involving electron-phone interaction. And in fact, what I also going to tell you is that most of the theories that have been developed around this time could be directly applied to most of the unconventional superconductor. And this is what is currently also happening, that the basis of multiple theories that are applied to modern materials can be traced back to 1972. So then there has been, for a long time, the unconventional superconductivity, which was discovered in heavy fermion compounds, was a kind of exotic beast because superconducting transition temperature was very low, and it also was limited to the to the 4F or 5F system until 1986, when Bernoulli and Müller discovered high TC superconductivity, and by now the highest transition temperature at ambient pressure is 135 and 160 under pressure. There is still one other material which was discovered around the same time, which has quite small TC, but nonetheless, we still don't fully understand the system, also partially connected because of the misinterpretation of some original experimental data. And there is still a large ongoing discussion on this system, but I'm not going to talk about it. So there is a large class of system which is known under the name of the ferromagnetic superconductor, and there are continuously new discoveries which are traced back to the beginning of this century, and it still continues until now. Now, in 2008, superconductivity entered, so to speak, the iron age because Hideo Hosono discovered iron-based superconductor, where the maximum superconducting transition temperature is of the order of 60 K. And last year, our community shaped by the discovery high TC superconductivity, but under pressure of about 14 GPa in bilayer. And as I'm going to show you, superconductivity in nickelates has a lot in common with superconductivity. Plus, before Harand 1, following some theoretical prediction dated back to the, again, 1999, has managed to synthesize infinite layer nickelates, which shows superconductivity of the order of 20-30 K. So as you see, the field is very dynamic, with almost new materials coming out, and of course there is a demand to understand them also theoretically. So why they are also quite interesting. So one of the main reasons why we want to understand unconventional superconductor, because typically superconductivity in those systems appear as a kind of a secondary phase to a magnetic phase. So if you look at the phase diagram of cuprates, iron-based superconductors, heavy fermions, ferromagnetic superconductor, which are shown here, you always see that there is another phase, and this phase is magnetic. So that is why they are also very, very distinct, and at the same time they allow you also to look into two quantum effects which are basically coinciding. One of them is superconductivity and magnetism. As I'm going to argue, you need really to understand magnetism in this system to understand superconductivity. Okay, so here is an outline of my talk. So I'm going first to give you a quick reminder on the layered cuprates, because let's say the basic ingredients of the, let's say, the most theoretical approach to that is really was developed for the layered cuprates. Then I'm going to discuss infinite layer and bilayer nickelates, which is new things, and they are mutually connected to the layered cuprates. Therefore, it's nice to talk about them. And also, this is for those of you who are also working on superconductivity, but maybe didn't follow this field very much in the recent year. And then finally, I will also spend some time, if the time permits. So, very good. So let me start with cuprates. But before before doing this, let me mention that again. I told you that the basis of non-phononic mechanism of the Cooper pairing was developed in the context of superfluidity in helium-3. So the first thing, what you know is that, as you know, in the solid Coulomb repulsion is screened. This is known under the name of Thomas Fermi screening. But you also know that because you have a Fermi step function at low temperatures, you will also get, in addition to the usual screening, you get somewhere some overscreening. Yeah, so if you look at the behavior of your Coulomb potential as a function of the distance, you will see that there will be tiny region where the Coulomb interaction gets overscreened. So it gets actually effectively attractive. And these are known under the name of the Friedel oscillations. Now, back in the 60s, when people were discussing potential possibilities of having unconventional superconductivity, they were speculating, and that particularly goes back to the Anderson, Pidaevsky, and Landau, that in principle, because again, if you make analogy with a hydrogen atom, you can form a two-electron bound state in a state which does not necessarily have m equal to 0, but have a other values of m, and then you can make use of this structure of the Coulomb potential in order to make it attractive just for one value of m. Okay, so that was the original idea, and then the first who did it rigorously was Kohn and Luttinger, who 1965 made the rigorous calculations by basically including the effect of the Friedel oscillation and asked what will be this contribution to the Cooper pairing. And so then they found out that at least for the odd value of m, so that means for the triplet Cooper pairs, they will be definitely attractive. But even for the m equal to 2, you will still have some superconductivity, but of course, that would be a ridiculously small superconducting transition temperature. I think they got something like 10 minus 11 Kelvin. And that was the first example of superconductivity from repulsion. So they was thought for kind of academic. Now, so it turns out that despite of the fact that this Kohn and Luttinger analysis was giving a small TC, nevertheless, if you put the estimate of the superconducting transition that you get, you would get of the order of 10 to the minus 3 of the Fermi energy. And that in Kelvin is 10 to the minus 3 Kelvin in the case of the helium-3. And that is actually in principle already quite close to TC in helium-3, which is of the order of 3 millikelvin. At that time, however, it was not realized because initial belief was that pairing in helium-3 should be a D-wave pairing, and therefore that was initially this Kohn-Luttinger mechanism ignored, but it actually turns out that it seemed to work quite well, in particular in helium-3. Okay, so now let's move on to the cuprates and ask ourselves, can we modify?
Ilya, could I interrupt you for a question?
Yes, please.
Am I correct for the helium? You have a strong short-range repulsion and long-range van der Waals attraction.
Oh, yes. Yes. So in principle, you need also to include, there has been another line of research where people were also including van der Waals interaction as a force for superconductivity as well.
And it provides a qualitative difference compared to the electron.
No, I think since it's known that it's m equal to 1, so I think you can combine both channels to give you attraction in the m equal to 1 channel.
Okay, thank you.
You can basically connect. So in principle, as long as you can also, that's also a question sometime for the community of the cuprate. So you can combine repulsive interaction basically by the presence of the Coulomb U, and you can combine it with electron phonon interaction. And as long as they act cooperatively, that is fine, as soon as they contribute to the same pairing channel constructively. So you can also have, let's say, positive constructive contribution to the D-wave symmetry, which is mostly driven by the electron, by the repulsive interaction. But for particular momentum of the electron phonon interaction, as soon as the order parameter doesn't change sign, it will also act constructively. So the most important is that you look for the right channel. Okay, so this is the cuprates, and okay, so let me, of course, mention to you that in contrast to helium-3, our cuprates are far from being a Fermi liquid. So what we know by now is that at zero doping, so that is basically for the concentration of, so the copper stays in this cuprates in the 2+ valency, which correspond to the 3d9. Which effectively in the filling means that you have d9 electrons on one hole on an x square minus y square orbital. And the EG orbital is also splitted because of the Janssen distortion, because you always have some orthorhombic distortion in this. So you have effectively a problem of having one hole on the half field dx square minus y square orbital. And that's what we know very well is by now is a well understood problem that in such a case you will form an insulator and an antiferromagnetic insulator because the electrons will not be able to move because of the Coulomb penalty, but in fact they can interact by the virtue of the virtual hopping back and forth, and that gives you an antiferromagnetic exchange, which is basically giving rise to the antiferromagnetic transition. And I noticed that Oleg Sushkov is also in this audience, and so let me tell you that Oleg was one of the pioneers in this field and made enormous contribution in this field. Okay, now let me mention further. So now, however, if you start to dope it, it becomes first a very strange metal. So you have also some strange pseudo gap, and we still don't fully understand it. However, if you go more and more towards the doping, so if you move, for example, to this region where superconductivity is about to disappear, but still pretty high, so you still have a transition temperature of the order of 60, 70 Kelvin. It turns out that in many respects, the system behaves like a good Fermi liquid. And this you can see by looking into the Fermi surface. Yeah, so one way of looking at the Fermi surface is to do photo emission. So where you basically use, by the virtue of the photo effect, you get an information about the electron band structure near the Fermi level. And if you see, you can nicely describe it by basically assuming that you have a single hole on a orbital on a d square minus y square orbital, which is hopping between, let's say, nearest and next nearest neighbors. And you clearly see that in this case, you have a very nice structures of, you have a photo emission, you have a quasi-particle peak, and you have a well-defined quasi-particles. Okay, so if that is the case, you can ask the same question. So you can take this Conn-Latinger mechanism and take the simplest model, which in this case will be a single band Hubbard model on the square lattice, which is hopping between nearest, next nearest neighbors. And then you follow this Conn-Latinger picture where you just include all the contribution from the particle hole, let's say, channel, which would give rise to a superconductivity. And you also, this is what the Fermi surface, what you get, and this is the gap equation that you need. And so what is happening is that, okay, so if you look at the structure of this interaction, you will see that it has the largest repulsion along the points which are connected by the antiferromagnetic momentum, because even in the itinerant picture, you see that the system is near the magnetic instability. And here you will see that this interaction will be, this Conn-Latinger will be peaked near pi pi. Since it's repulsion, you cannot solve it for the S-wave channel because you need to overcome this minus in the gap equation. And so what you do, you effectively overcome this minus by changing the sign of the superconducting order parameter from position K prime to K. So you start with a plus, and then you go to minus, and then you again go to plus, and then you go to minus. And it turns out that in this case, the most natural position appears to have a d square minus y square. Okay, and again, that there has been quite a bit of research, again, from the side of, let's say, weak coupling type of theories. You can do also, there has been development in the functional RG by Zelashinsky, Yakovenko, originally Schultz and Leder, and later also by Metzner and Honerkamp and collaborators. And they all give, they are consistently giving the dx square minus y square symmetry of the superconducting order parameter for, let's say, increasing range of complexity. Okay, so now let me also mention that there is no doubt that the symmetry of the superconducting order parameter is d-wave because it's a well-established phenomenon. Because with photo emission, you can not only measure the Fermi surface, but you can also measure the superconducting gap because you have a Bogoliubov of quasi-particles and there is a gap opening at the Fermi surface, and this gap will be angular dependent, such that there will be a minimum somewhere, because what is happening is that in order to come here from minus to plus, you'll certainly need a zero lines here in between. Okay. And this is what has been measured, and you know that has been already awarded by the Oliver Buckley Prize to Campuzano, Johnson, and Ziegfeld. You can also do Josephson experiment, and in this case, you take an advantage of the fact that your superconducting gap has different signs, and we know also we can also write the superconducting gap the function also in the real space. And then you can construct your junction in such a way that it will connect. For example, if you take an S-wave and a D-wave superconductor and you put it in contact with each other, you expect a very different behavior of the critical current. And that has been also confirmed by a number of experiments. Therefore, I don't think there is any doubt that the symmetry of the superconducting order parameter is D-wave. Plus, there has been further development by Fourier transformed STM, which is also has shown unambiguously that the symmetry of the superconducting monoparticle is given. Now, you can easily extend the theory, so you're going beyond Berg-Schiffer. You just simply include all, not only just the second order perturbation when the theory is not conformable, but you can just sum all the diagrams in the same, let's say, the same type. So you do an RP type of summation, and then this is how, in this case, the effective interaction change. And then what you see is that, in principle, by looking in its form, you now realize that it contains of the two terms. One is spin susceptibility, another one is the charge susceptibility. And obviously, for positive U and for paramagnetic state where your susceptibility is positive, you see that the system likes, so the closer the system is to the magnetic instability, the higher, let's say, the large instability in the superconducting state also will be. But of course, it will be a secondary instability. And that is, of course, that is why this mechanism, the repulsive mechanism, I also sometimes call magnetic mechanism. Nonetheless, after saying this, let me mention something which probably after more than almost 40 years research on high TC cuprates, I have to make a commitment that despite the fact that we can relatively nice describe the superconducting gap, and we also can relatively well describe the antiferromagnetism as being a result of the Mott insulating state and its evolution upon doping on the electron and fold up side. The rest, we don't know very well. So there is, and the reason is that the behavior of the quasar particles in the normal state is not well understood. Firstly, because we still don't know the origin of the pseudo gap, but also because there is an ongoing discussion how well are defined quasar particles. Are they really quasar particles? And that is all the questions that are still discussed in this context. Nevertheless, as I said, surprising fact is that the dx square minus y square is let's say, is unambiguous. And let me mention that what I was presenting to you is, let's say, extension of the Korn-Lattinger theory. But you can also try to do it from the other side. So really start, in this case, there is no, let's say, control theory. Of course, you can do a TG model, but unfortunately, you can start from the Mott insulating limit and discuss how superconductivity emerges upon introducing doping. That's one thing. But in that case, you can also do certain things analytically. But what people also do is they do numerical method. So that's so ideal experiment. So they start from a Hubbard model and then try to solve it. Hubbard model on square lattice, and then try to solve it with various exact techniques, but which are, let's say, only allow you to look at the final size approximation. Or you can basically do, which is known under the name of dynamical mean field theory or dynamical cluster approximation, where in this case you try to reduce the correlation only to a single side, so when you have a class of non-interactive for the particles, and there is still only on one side, there is still an Coulomb term. That would be exact mapping to the Anderson type of problem. But meanwhile, the various groups have managed to include also let's say, several. So where they include a cluster of such strongly correlated impurities interacting with a bus and analyze what's happening in this case. And what is surprising is that they always get a D-wave symmetry to be a dominant instability near the n equals 1. Okay, so that is, so once what we did in the relatively recent past is that we started to basically combine our efforts with dynamical cluster approximation and with, let's say, doing Korn-Lattinger and RPA. So you can relatively easily map out the symmetries of the superconducting gap. And again, I told you that the dx square minus y square symmetries are the main near the n equal to 1. So that is where you have here. However, once you go from n equal to 1, you get all kinds of different symmetries because it becomes an interesting interplay between, let's say, Fermi cell topology and structure of the spin response where the main peak is occurring. And then you can look which other instabilities you have. And then what you can do, you can take one of these points, which you can get relatively cheap with this weak coupling of series. And then you move to exactly this point in the phase diagram and do dynamical cluster approximation. And what you surprisingly see is that there is a continuity of the leading instability, which is changing as a function of U. So you can look not only on the main instability, but also on subleading instability. So that means that despite of all of this complication in the system, and in fact, in the dynamical cluster approximation, you don't have a well-defined quasi-particles because you can also get a pseudo gap and so on. Nevertheless, the tendency towards the bound state, Cooper pair bound state with a dx square minus y square symmetry is a universal phenomenon independent on the strength of the interaction. Okay, that's all what I wanted to mention about the cuprates. And now let me move to the infinite layer and bilayer nickelates. Okay, maybe, I don't know, does it make sense to ask if there is any question to the cuprates, Dimitri, or should I just continue?
Let's ask the audience just.
Hi, Ilya, this is Oleg.
Hi, Ilya, yes. Very nice.
I have a question, just if you allow, about cuprates. Can you comment on RPS data from Takeshi Konda? Small Fermi surface.
On the optimally doped, or where the
No, underdoped.
Oh,
small Fermi surface.
Yeah. So the thing is that, as I said, that that in the, let's say, in this region, in the underdoped, the Fermi surface is by far not the one which I've shown to you before. That's maybe for the. So this you see only in a well overdoped regime. Whereas if you go towards underdoped region, you do not see developed Fermi surface. Sometimes it's known under the name of Fermi arcs. So that means that you have some well-defined, relatively well-defined, let's say, quasi-particles around the diagonal of the Brillouin zone. But as soon as you go away, the spectral weight kind of becomes eaten up. And there is still a discussion whether you see really a pocket, because in principle, if you would have some magnetic order or kind of magnetic order, you would, or strong magnetic antiferromagnetic fluctuation, you would form pockets. And this is, I think, also not only Takeshi Konda, but Peter Johnson was claiming also to see in the underdoped cuprate.
Peter Johnson is always ambiguous, but Takeshi is unambiguous, and he sees it even in disordered phase.
Yeah, okay. Yeah, so that in principle would tell you that if you have a pocket, that to me looks like you have another phase, which is changing the Fermi surface topology. It could be related to some translational symmetry breaking. It could also very well be that you have some additional or order which would yield the pocket. But in order to get a backward, so in order to get a pocket, you need to have this part, and this should come from some folding of something, if I understand your question right. What I can What I only can tell you is that you can, and this is something that people were doing, and also I was doing that too. So you can try to play around what is happening if you, for example, introduce another order. Like we know that there is a region where antiferromagnetism and superconductivity coexist, not in the whole dot, but in the electron dot cuprates. And you can look how the U activity changes if you move towards the top. And even in that case, it turns out that the D wave still appears to be the dominant solution, except that the D wave in this case will have not a maximum of the gap here, but will have somewhere here. Okay. I don't know what else do you want me to comment?
No, my question was more related to the experimental status, because on the one hand, Takeshi, it seems that Takeshi unambiguously shows small Fermi surface even in disordered phase. But on the other hand, I know that some RPS experimentalists who did not see this for 20 years
Yes.
They're skeptical about his measurements, and I'm
Yeah.
curious about your comment.
I have to admit that I don't know whether it has been resolved. Like it's frequently happens in this field of ITC, that people stick to their observations and don't want to agree. What I tell
It's
you,
not only ITC, it's general human nature.
that's true. Yes, but okay, so there is another part which I didn't want to enter. It's very interesting, but it's far from being well understood. This is why I didn't want to talk about this. So, for example, for a while, ARPIS was the only method that could see a Fermi star. Recently, or relatively recently, it turns out that you can also measure the quantum oscillations with a good quality of the crystals, and they actually reproduce in the overdop the result of the photo emission. But in the underdop, they get a result which, let's say, under strong field, I mean, you have to know that you have to apply a large field of 50, 60 Tesla. Under these fields, you start to see something, you see some quantum oscillations, but the sizes of the Fermi surfaces that you get from these oscillations, they do not make any sense if you compare them with ARPIS. Therefore, it is very likely some other phase which appears once you are entering in a strong magnetic field. But what is this phase? People still don't fully understand, because it cannot be just a folding, it cannot be just a simple charge or spin density wave phase, because the sizes of the pocket is far too small. Yeah, but you see,
Yeah, my comment, it's not what Takeshi claims. These are very recent measurements. Last year, he
Yes.
claimed that his quantum oscillations are perfectly consistent with ARPIS.
Consistent with. Okay, so yeah, that's interesting. And this is on which system? On
This is multi-layered. I'm always bad with compound. Multi-layered mercury. If I
okay,
remember.
so that's a
Yeah, maybe we could shift the discussion
okay.
to the end of the talk.
Right. Let
Okay.
me move on.
Sorry.
Okay.
Debate.
Yeah. Okay.
Perfect.
Very good. Okay, so now let me say, so what is basically the basic lesson you learn from the cuprates? You want to have a single d square minus y square orbit on the Fermi surface, or close to the Fermi surface. And then there was been more or less immediate theoretical suggestion that is going back to this gentleman, which suggested, well, can you take a neighbor to the copper and take nickel? However, if you take it in oxides, that would be also nickel 2 plus, but this would be 3D8. So you need to go to the nickel 1 plus. To get nickel 1 plus, you have to get rid of the apical oxygen. And the only natural materials that you can have is the so-called infinite layer, where with this formula, where you have a rare for the rare earth compound. And in that case, they have been shown theoretically, already based on the DFT, that indeed you would get a d square minus y square orbital, but in contrast to the cuprates, you don't have the charge transfer gap is really large in this case. And in this, what is actually happening is that there is a 3dz square minus r square orbital that is also near the formula. And you need to get to synthesize this compound. So it has taken, after this theoretical prediction, has taken really a decade, more than a decade, almost 20 years, to make an experimental realization. That has been done by Harald Huang and his collaborators. But let me mention, there has been really many groups. I mean, in Germany, for example, there was one department which was working on the nickelates. Bernhard Keimer was also trying to get this system. And the idea that Harald Huang pursued is that they grow the thin films of the neodymium nickelate on the substrate, which is strontium titanate. And of course, what you first grow, you grow the usual perovskite, and then you do some topotactic reduction by basically using calcium dihydride to get rid of the one oxygen. And this is how they successfully managed to do it. But in order to make it superconducting, of course, you have to first dope with the strontium and only then do a topotactic reduction. And this is what they succeeded at the end, and found that the superconductivity is about 10 Kelvin. Now, already from the first experiment, they saw some indications that that the system is not just a one band. However, So that was debated until really last month, where the first ARPIS data were appearing by a group from China, which has shown that indeed the original prediction has been correct. What you see is a dx square minus y square orbital dispersion, so the cuprate-like electronic structure with some extra contribution of the dz square orbital. And by looking at the renormalization of the quasi-particle, by looking at the change of the Fermi velocity, the value of u that they subtracted is of the order of 4 electrons, which basically immediately tells you that you don't, it's relatively well understood, so what is going to happen. So, you know, we did the calculation for the system without yet knowing the ARPIS data. And at that time, we looked what happened if you have both dx square minus y square and the dz square orbital and apply the same mechanism that I already introduced to you, which need to be just extended to the major orbital case. And you do all that, of course, as soon as you have mostly dx square minus y square dominant and coherent, you will get the dx square minus y square orbit to be present at the Fermi surface. What about the experiment? Well, experiment is kind of consistent with the dx square minus y square, because if you look at the penetration depth, it shows a nodal gap, which would be consistent with a dirty D wave fit. You can use various rare earths, and it appears to be roughly consistent with dx square minus y square, apart from the neodymium system. There has been some surprising data on the STM, which has shown that you see two types of the gaps. One of them is V-shape, another one is a kind of a U-shape, but one can nicely show that it can be all an artifact of just distributing a D wave on a different bands, one band which is dominant and the other one will be subdominant. Okay, so after that, the main efforts were taken along the direction of getting D9 or close to D9. There has been various attempts to take a Rodelson-Popper series with reduced oxygen to get to the doping which would roughly correspond to the 20%, where people thought you should have an ideal situation for superconductivity. That has been halfway successful, but of course you understand that the more complicated, the more number of layers is increasing, the more complicated it becomes. But TC was not rising. Now, there has been a surprising result on the first glance, which came from the last year by Meng Wang group from China. It was actually just growing bilayer nickelate to look for potential magnetic structures. They applied it also pressure, and then surprisingly they found it's superconducting, and superconducting transition temperatures of the order of 70 Kelvin. But before you get superconductivity, there is also a structural transition around 12 to 15 GPa. And what is surprising is that if you just look at the counting of the formal configuration of your nickel valency, you get a 3D 7.1 configuration, relatively, so actually far away from 3D. So that, so you first need to understand what is going on. You need to understand what kind of structural transition it is. And the structural transition is basically changing. So you have this nickel O6 octahedra, and in the low pressure phase, the angle between this octahedra is 168 degrees, whereas under pressure, the transition takes place and the angle becomes 180 degrees. So which basically means that there is a large hybridization of the 3dz square orbital along this line with the oxygen. Okay, very good. So that then afterwards, people have looked also what happens to the trilayer, and they also found the same effect. So again, it becomes superconducting, transition temperature of the order of 25-30 K. There is some issue about the volume fraction of superconductivity in bilayer nickelates, which is by now settled by 50%. In trilayer, it's 100%. And again, the same transition, you need to have an ideal angle of 180 degrees between the architecture. Systems are magnetic, so there is a magnetism found in both of them. So it's again telling you that there is a necessary prerequisite for the unconventional superconductivity. So in this case, this is a metallic spin density wave. In view of time, I will not discuss the details. So now how it comes that despite of the fact that you have a 3D 7.5, how does it come that at the end you end up with having more or less again a single hole on the dx squared minus y squared orbital? Well, what do you have to take into account? You have to take into account the bilayer structure and the fact that you have a bonding antibonding orbitals. And if you do this, if you do the counting of this, you actually end up in the situation that you have almost a field. So you have a bonding antibonding dz square orbitals, and you have a dx squared minus y squared. But what is happening is that at the end you are left with one dx squared minus y squared hole, and almost occupied, well, so in a single, let's say, spin picture, in the insulator picture, that would be fully occupied, and the other one would be empty. If you do in a metal, then the situation will be a bit different. But what is again most important is that you get the desired configuration. Now, this is the Fermi surface that you expect in this case. So, and in order to understand, now you look. So this is your. So now it's very easy to understand for those of you who worked with cuprate. So imagine you have a dx squared minus y squared orbital, which is now splitted by bilayer splitting. Now, in contrast to the cuprates, where the splitting is small, here the splitting is quite sizable. So you have a large splitting, but it's still degenerate along the other direction. Plus, you have still some residual of the 3dz squared minus r squared orbital. So the one which is, let's say, in the bonding orbital, which is still crossing the Fermi. Nevertheless, if you look at the Fermi surface, it looks very two-dimensional along the case. So in order to understand further which type of symmetry of the superconducting order takes place, you have to, and by the fact that it looks very two-dimensional, so what you just need to do, you just have to repeat the exercise which was known for the bilinear cuprates. So you start with, let's say, bonding and anti-bonding state, and you separate your states, your interaction oxygen into the bonding and anti-bonding part. And then you also look at the susceptibility, such as even an odd channel, which consists of scattering between antibonding or bonding bands, or antibonding and bonding bands. Okay, so then what you do, then you compute your response, particle hole response in both channels. And you see that there are peaks in the various channels. So one of them indeed corresponds to the one which is found experimentally. But what is the most important is that what you need to check is the absolute magnitude, whether the largest susceptibility is in the odd channel or it is in the even channel. So if it is largest in the odd channel, so obviously what will happen is that you will have a largest repulsion between these bands, and that will be the one which will be driving the sign change. So that will be an order parameter which is changing the sign between here, and it will be an S plus minus. This is so-called bonding antibonding S plus minus. And this is what has been immediately found in a number of theory calculations. However, again, it depends on how many hopping parameters you include in the plane or between the planes. So if you include a larger number of hoppings in the planes, then your susceptibility gets of the same order. So it means that this bonding antibonding S plus minus gets frustrated, and then your natural solution becomes a dx squared minus y squared solution. Okay. Okay, Dimitri, how I'm doing? Do I still have time to talk about iron base?
Sure, we are happy to continue.
Okay.
Maybe do we have any
question on the nickelates?
Nickelates? Maybe quick questions.
So now maybe a final remark.
May I ask a very quick question?
Yes.
Are there any RIGS data for nickelates to estimate?
Yes. So I was quickly citing this. So this is this one. So this is so there is a RIGS data, which the RIGS data there is because it's an ambient pressure, you can do it very nicely. There is RIGS, neutrons, and also Mirsat data, which all point out that you have a pi/2 spin density wave order.
And what is the value of J from RIGS?
That is, let's say, about, I would say 60 millieV.
Thank you.
60 millieV. Yeah, so that's maybe what I should also mention for the infinite layer nickelates. People have done the measurements also on the infinite layer, and they fitting this with a Heisenberg type of model, you get also the order of 60, 70 million.
So it's twice smaller than cuprates, and critical temperature is also twice smaller.
Kind of, yeah. I mean, again, there is still material dependence. I would say for the bilayer nickelates, it is of the order of bilayer cuprates. So it's of the order of 80 Kelvin, but you're right. I mean, one could connect it to this. Yeah.
And I have a question. So you discussed bilayers, but what about monolayers?
Lanthanum 2
activity?
nickel, lanthanum nickel 2O4. This is known to be a Mott insulator. So this do not manage to dope. People didn't manage to dope. It doesn't become superconducting. It's an insulator.
And what about 3-layer or few-layer systems?
So the 3-layer is also superconducting. This is also shown here. So they are very similar to the bilayer. They also show superconductivity. So that's for the tri-layer. For the 5-layer, I don't think that has been any reports yet. But if you believe that the same physics is in play, usually yes, except that again raises a question, which type of symmetry? Because the more layers you get, the more problems with bonding, antibonding, S plus minus you start to get. Because if the symmetry is bonding, antibonding, S plus minus, like it is here, in a tri-layer, roughly you can understand the structure as bonding, antibonding plus non-bonding band. So imagine you have another band somewhere. And then, of course, to put an S plus minus there would be again difficult. But if you get a D wave, there is no problem to that. Except that there is again a little bit frustration because the more Fermi surfaces you put, there is always this question of the fixing the relative phase of the order parameter between different Fermi surfaces, and that introduces another frustration component.
Okay, thank you.
Yeah. Okay. Now let me go to the iron base. So so these are materials which were discovered in 2008. They also have a late structure that is, however, iron arsenic or iron selenium. They have also show a very similar phase diagram to all the other unconventional superconductor, magnetic, which adapt as a spin density wave transition. There is also a structural transition known under the name of pneumatic order because it's believed to be driven by the electrons. It becomes superconducting upon electron and hole doping. And then you look at the Fermi surface, well, these are your hole and electron pockets. And you do exactly the same game. So the first game you see, you do the Korn-Latinger analysis, and immediately you realize, well, so in fact, this picture is very simple. So you look at the Fermi surface, you know where the largest interaction comes, where the largest repulsion comes, and then you just need to set up the order parameter such that it changes sign between the largest repulsive indices. So that immediately gives you an S plus minus. And that has been again very well seen in the experiment by various groups, including mentioned today Takeshi Kondo, who sees that the gap is a constant on both on hole and electron type of the Fermi surface. There is one issue, however, is that there is still no direct evidence, in my opinion, that the superconducting gap is changing sign. I mean, in other words, there is an evidence in my view, but you need to do some calculations. And one of these is that what you need to show is that once the superconducting order parameter changes sign, there is a claim by theorists, including that in this case, the Bogoliubov coherence factors, because you have a Bogoliubov quadrat particles, will start to behave different compared to the conventional superconductor. And then all of a sudden, when you break a Cooper pair into this particle hole excitation at 0 temperature, suddenly this you will get an additional enhancement below this, the twice the superconducting gap magnitude. And there is an experimental indication that this is exactly what is happening, but you need to measure the superconducting gap on both and show that you are really, that your threshold is above the peaks that you see in the neutron scattering. And there has been some experimental evidence in favor of this. Of course, the physics of iron-based superconductor is also multi-orbital. You can all include that. So in this case, you actually have all T2G manifold, which is near the Fermi level. So that means that you cannot really play just with Coulomb U. You have to include all the Hubbard-Hund type of the interaction, and that has been done in the field. So people have been looking on all that, and it actually turns out that despite the fact that the mechanism is universal, but the superconducting gap magnitude and whether or not it's nodeless or nodal is not. And it basically depends on the interplay of the order parameters. So you can have a gap which being constant on hole and electron type of the Fermi surfaces and being roughly a constant, but opposite sign. You can have one being roughly a constant, but another one will have basically some angular dependence and even crossing the Fermi level. So you will have a nodal behavior all of a sudden, but these nodes will be accidental. You can even remove them by disorder. Or you can, if repulsion is not, if let's say you have a situation where the gaps will have deep minima and maxima, but no nodes. So in principle, that was kind of surprising to the community because initially, 20 years ago, observation of the nodes or no nodes meant a completely different mechanism. While here it's the same mechanism, but what only changes is how strong is repulsion between the band compared to the one which is within the bands. And depending on their ratio, you can get one of the three. But the superconducting gap is still S plus minus. And in fact,
Yes. Could I interrupt you? Am I right that this right picture corresponds to the superposition of S and D?
No, you are not, because you see this as a this is not, because what you need to know is that so these are located at the different parts of the Fermi surface. This is near the gamma point that still stays always more or less a constant, but these are located near the M point that has a lower symmetry than the gamma point. So therefore, when you have a node there, so the position of the nodes does not coincide with D wave. So it's really accidental nodes. So if I again come back to the Fermi surface, so imagine you move on the Fermi surface, and then somewhere, for example, here, you have nodes, but these nodes are not a D wave. So they still can be described by the irreducible representation of the cosine kx plus cosine ky. Just expanded. Imagine that you expand this function near the M point, not near, because near the M point, the cosine kx plus cosine ky becomes cosine kx minus cosine ky. You understand?
Yeah,
because
okay.
at pi 0, right? So that, yeah. Okay, so that's still an S wave. So, okay, so just the last few words, maybe on the most actual results. So, so you can understand relatively well all that phase diagram. So with the whole glory of the theory, even to the extent that you can even ask some interesting questions. So what happens if you dope the system such that you remove one type of the carriers completely? For example, you remove completely electrons from the Fermi surface. And this is happening, for example, in the barium potassium. So then what is expected that you should, if the same mechanism works, the repulsive mechanism, you should change from S plus minus, where the whole, the pluses are on the whole Fermi surfaces, and the minuses are on the electron Fermi surfaces, to the situation where the order parameter changes sign between two inner hole pockets. But this is, of course, here, if you go at high temperature, there is no problem to do that. However, if you do it at lower temperatures, if you go it along this line, that is, of course, means that your phase, relative phase of the order parameter may be other than just 0 or pi. And this is, so you have some intrinsic frustration of the situation when you have electron and hole pockets. And so it means that the relative phase will have to change between A and B from 0 to pi, but it can change continuously, which allows you to have a time reversal symmetry S plus IS state. That has been also observed, and this is the one which is currently under investigation, and there has been several nature physics on this, where people indeed observed the breaking of the time reversal symmetry by muons in this region and trying to figure out the details of this state. Another interesting system, and this is the last couple of slides, is iron selenium for several reasons. So the first reason is that the Fermi energy of these systems are very small. So you always have this pocket, but here they are extremely tiny. So E Fermi is considered this is energy which is separating the top or bottom of the electron or hole band from the Fermi level. Yeah, so it's really that tiny numbers. Okay, now furthermore, it doesn't have antiferromagnetism. In contrast to the other iron-based superconductor, it doesn't have antiferromagnetic transition. It only has a structural transition, which is not dubbed by the name of pneumatic transition, and you have superconductivity built. This system was in the focus of research over the last, let's say, 5 to 7 years. So what is very interesting is that people have been looking really in details of this and characterize the sizes of the Fermi surfaces. And so they know how to characterize also the Fermi surfaces in the pneumatic state. All that has been very well characterized and understood. So again, a very surprising fact is that you have an E Fermi of the order of the superconducting gap, which immediately tells you that your conventional BCS type of theory cannot be applied. And the sizes of the gaps you can measure, for example, from the fully transformed STM, where you measure the scattering interference, quasi-particle interference from Bochum quasi-particles, and you can nicely estimate the sizes of the superconducting gap, which actually tells you that in order to understand, although it's an F price minus superconductivity, but what you need to do, you have to work in the anti-adiabatic limit, which basically, you know, in the conventional BCS theory, you assume that you have a Fermi energy, which is much larger than the characteristic energy of omega debye, h bar omega debye. So that would be conventional. So this is your energy formation of the Cooper pairs. This is your Fermi energy. And this is upper cutoff, energy cutoff, so basically your bandwidth. Whereas in the situation of the iron selenium, you have a situation where your E Fermi much smaller than the energy of the formation of the bound pairs. So that tells you that you first want to create the molecules and only then get a condensation. So something which is known under the name of BCS-BC crossover. In fact, we have studied this. However, it turns out that an iron selenium pure is only on the verge of this BCS-BC crossover, and partially this is connected by the virtue of the compensated semi-metal. So here would be a temperature where the bound pair forms, and here would be a superconducting transition temperature as determined from the superfluid stiffness. And it seems that indeed iron selenium is close to the limit. And in order to get a crossover, you need to do something. So like, for example, apply pressure or dope the system. And this is where you really can see the crossover. However, in a pure iron selenium, you don't see that. And this has been also confirmed experimentally in the STM, where they didn't see a pseudo-gap features. Okay, good. I am thinking that I probably stop now. So there's been some discussion on the effect of the pneumatic fluctuation, but I will jump now to my conclusion and tell you that I tried to give you some update or that status report where we are with respect to the understanding of the superconducting gap symmetry in various unconventional superconductors, but basically 3 classes: cuprate, nickelates, and iron-based superconductors. And so this magnetic mechanism, you know, I gave you one example of it. You can on a weak coupling, but you can also do it on a strong coupling limit as well. But this mechanism give you a good understanding of the symmetry of the superconducting order parameter. From cuprates to iron-based superconductor. In nickelates, there is still no confirmation experimentally which symmetry is going to be. But there are 2 candidates. Also, this theory nicely explains many other systems, but fail for some others. So there's notable examples where this theory, for some reason, do not work, and this is where people are puzzled. And the theory cannot predict the rigorous value of TC. because we don't have an effective description of the bad metal normal state in most of the cases. So the current estimate is that we have a TC of the order of 100K in cuprates, which is an estimate from the either cluster DMFT, or there has been some attempts to get a superconducting transition temperature from measuring the spin excitation spectrum and plug it in the corresponding equation to get a TC. They all give in the order of 100 Kelvin. Okay, and at this point, I would like to stop and thank you very much for your attention. And I'm happy to take questions. Sorry for being a bit late.
Okay, let's thank you, speaker, for fantastic talk. And welcome questions. Please just go ahead and ask. Maybe I can start. So if you have a few superconducting order parameters, does it result to a new collective modes, like a Leggett mode for the two-band superconductor? Have they been reported?
Yes.
Many of the systems?
Yes. So that is, of course, the whole plethora of novel excitation that you can get in a multi-band superconductor. So there has you can have a Leggett mode, which is a mode related to the relative phase of the order parameter between both. Also, because in many of these systems, there are different symmetries which are competing for, let's say, for winning the Fermi surface. You can have an S-wave, extended S-wave order parameter realizing, but the D-wave will be a subdominant, and then you can have a Bardassi-Schrieffer mode. You can also, you have various, I mean, if you compute the fluctuation spectrum in the superconductor, it's extremely broad, and there has been experimental identification that such modes were observed. That's true.
Do you have any interesting in this when you have these three order parameters with frustration?
Yes.
Does it provide any special to collective modes between?
Yes. So that is what you get. So you will get a particular mode related to this S plus IS state. We actually worked with it with Maxime D0 on this, so we have a paper on this.
Okay, thank you. Any other questions? Please just go ahead, unmute yourself. And...
May I ask another question, please?
Yes.
Welcome.
Ilya, could you please show your slide just before iron selenium?
This one?
This one. This is a picture when you have a B and A, two Fermi surfaces, nothing else.
Yes.
And are you saying that in this case, one can have superconductivity?
Yes. So there has been, okay, so you have B and A, only hole pockets, and it's known that it is superconducting. So you have this is a barium potassium. So you can completely substitute barium by potassium. So you have a potassium, iron 2, arsenic 2. That is completely hole substituted. And it doesn't have electron Fermi surface. It has only hole Fermi surface.
And what is the mechanism for this, for superconductivity?
So the mechanism is that you have a repulsive interaction between the two hole pockets. However, this interaction is of the same order as the intraband. Right. And so what is happening is that exactly what I was showing before, that what is happening is that the only way you can get superconductivity in such a case that you will get roughly a constant on one and this overall minus on the other, but it is actually strongly angle dependent. So such that an average value of it is very tiny.
But critical temperature 38 Kelvin.
Will be very small, 3 Kelvin. And this is exactly what is
3 Kelvin.
3 Kelvin. Yeah.
Interesting, because you have this in whole doped gallium arsenide for free. This
type of the Fermi, but you need, of course, you need to have a repulsion, right? So in gallium arsenide,
Coulomb repulsion. There is Coulomb repulsion between holes, right? That's no doubt.
No doubt. But well,
we did try to find, because we have been looking for superconductivity in the system, but it seems that that doesn't work.
Okay.
Interesting, but okay.
Okay, to tell you the truth, So there has been this year, so this picture is a bit outdated. But to tell you the truth, there is another but whole Fermi surface located somewhere here that has been recently identified by the ARPIS. So there is another whole pocket located somewhere here, here, and here. So in reality, but they are all whole-like. So maybe that's something that helps.
Mm-hmm.
Yeah.
Okay, thank you.
Any other questions? Please just go ahead.
Hey, hi Ilya.
Hi, Stefan.
Thanks for the nice talk. That was cool. I have a question. Slightly, you know, when you told us all these things about the cuprates, nickelates, and so, now what about P-wave superconductivity? With all the knowledge you have, if you had to start looking for a P-wave superconductor, what would you do? So, what is the insight about that?
Well, you see, the surprising thing about this theory is that it always wants to give you, and that is also maybe something that is related to original belief by the theorists in 60s by P.W. Anderson, that this type of theory can give you relatively easy even parity states, which means D wave or anything which is extended S wave, D wave. For the P wave, I have to admit that in all my, let's say, calculation in the past, as long as you do not include a spin orbit coupling, there is no way, essentially. Because you need some uniform attraction for small momentum. And that is what is more or less given in helium-3, but in the solids, there is always a problem because we know that there are crystals and the symmetry is lower than the fluid, and therefore there is always some preferred, in crystals, there is always some preferred direction for the scattering, typically along the bonds, and that is usually always likes to have an even parity superconductivity. So I would say you need to go to the system with spin orbit coupling, in my opinion. I mean, like strontium ruthenate, but even in the strontium ruthenate, there is essentially just a confusion. It's just so confusing because you know, just for the experts, I can mention that for some time, my understanding was that after the P wave, or let's say after the P wave or triplet superconductivity has been excluded, I thought that the most simplest explanation or the plausible explanation was put forward by Jörg Schmalin and collaborators, where they said this is accidental degeneracy, which is further bounded by the presence of dislocations, which bound, let's say, or act as a seed to have this accidental degeneracy with time reversal symmetry breaking. However, there has been some experiment where they measured the number of dislocations in the crystal, and they cannot really account for the effect. Yeah, so that still remains puzzle. Superconductivity is two-component, breaks time reversal symmetry, but it's very likely not triplet. Yeah.
Okay, thanks.
Yeah.
I have another question. So, for in the V coupling regime, as I understand, the conventional superconductivity is super stable to disorder, but unconventional one is quite sensitive, as can be described by some kind of extension of Abrikosov.
Yes.
Yeah. So how these arguments are avoided when you have this strong coupling series?
Yeah, so that's a very good question. So let's say in the context of the, let's say, iron-based superconductors, there is an easy answer. So the sign change occurs for large momentum transfer between pockets at the gamma and the pockets at the endpoint. So the only effectively pair breaking scattering in this case will be only those scattering which scatter from gamma to M due to the impurities. However, we know that from the potential impurity are usually acting on these are Coulomb centers, and then they are acting at small momentum. For the small momentum transfer, this still holds that the order parameters still have the same sign, Therefore, there is no effect of, so that's relatively robust to the potential impurity scattering. However, the general answer to your question, yes, unconventional superconductors are more sensitive to the potential disorder than conventional superconductors, and it's known. There is, let's say, there has been study in this regard, and they all show, let's say, behavior which is consistent with Abrikosov-Gorkov formula for magnetic impurities, but here it will be like magnetic. Now, for D-wave, there has been an ongoing discussion that why is D-wave still survive despite of the, let's say, strong disorder. And again, the answer comes that according, again, you have to trust the theorists who are telling you that if you compute the dominant term in the scattering, they're consistent with the dx square minus y square symmetry. So it means a particular dx square minus y square symmetry will be robust, but it requires some, I mean, there is no universal answer to that, Dimitri. So you have to look into the details.
But will reduce the critical temperature, so
of course
say,
they do.
Eliminate disorder. In this
Right.
case, the temperature is supposed to dramatically grow.
Yeah, supposed to rise. That is true. I actually don't know whether there has been any study on this, systematic. The problem is that in the oxides, the main issue is that nobody really knows the number up to, you know, up to 5%. Nobody can tell you how many oxygen are inside. Okay, so in this regard, it's not the best system to study the disorder. In iron-based, the study with electron irradiation has been done, so that at least they could show that you can reduce TC according to the Abrikosov-Gorkov formula. I don't know whether there have been attempts to systematically study whether you can increase TC with respect to the residual resistance ratio. Might be that exists, but I'm just not aware of it.
And just for my education, am I correct that these systems are relatively dirty? I mean that gallium arsenide and graphene, they're clean, perfect systems, but compared to them, these are very...
Yeah, I mean, of course, these are just dirt for the semiconductor community. They, I mean, there is no chance people who work on semiconductor and they reach this level of purity of their system, they, of course, would not look into the working with this system. But again, you know, my answer to that usually would be yes, but because of the collective quantum phenomena, you know, the superconductors, I mean, we use superconductor for building quantum computers. So the fluxon qubits are the, let's say, the basic elements at the moment for quantum computing. Despite of the fact they might be still quite dirty, right? But because they are superconductors, that basically removes all the complication. So this is why you are looking also for high superconductors, because you think, well, they're dirty and maybe material-wise not that clean. But once you are able to manage to make superconducting, all that doesn't matter, because superconductivity is robust in many respects with respect to impurity, so you just can use it. And that's generally this general take on correlated electron.
Okay, thank you. Do we have any other questions? If not, let's thank Ilya again for great talk.
Thank you so much, and yeah, see you next time. Yeah,
yeah, and see you everyone in a month. Bye, Ilya. Bye, everyone.
Bye. Bye.